All right, so now we have set the stage. We have a resting membrane potential. We have an electrical chemical gradient that makes the cell excitable, and that gradient is maintained by those leak channels and by active transport of potassium into the cell and sodium out of the cell. Okay, we have that. So we've set the stage. So now we've prepared the membrane for changes in electrical potential. So electrical potentials within each neuron conduct information in a predictable and consistent direction. So the conduction originates with local potentials at the receiving sites of the neuron, and in a sensory neuron, the receiving site is a sensory receptor. In a motor neuron or an interneuron, the receiving sites are on the postsynaptic membrane. So the initial change in the membrane potential is called a local potential because it only spreads a short distance along the membrane. This diagram from the book shows, basically it shows the path of what happens when we're transmitting sensory information along an axon, starting with a local potential change and developing into an action potential. And so the sequence happens per this diagram. A peripheral pressure receptor is deformed. So maybe you sit on a chair and you put some pressure, or you apply soft tissue mobilization and you put some pressure and you deform a pressure receptor. The change in local membrane potential in the sensory ending creates a local potential. If there are enough of those local potentials, you generate an action potential, which then propagates down the sensory axon. It releases neurotransmitter from the presynaptic terminal. It binds the neurotransmitter to ligand-gated channels on the postsynaptic terminal, and it activates potential in the postsynaptic membrane and on down the chain. So local potentials are that initial change in membrane that only spread a short distance. Action potentials, they change, there's enough of a change that it results in depolarization. So it's a large depolarization of electrical potential, which allows it to be repeatedly generated down the line. So local potentials are categorized as either receptor potentials or synaptic potentials. Receptor potentials are generated at a peripheral receptor, and synaptic potentials are generated at a postsynaptic membrane. So local potentials can only spread passively in a small area of the membrane. So the peripheral receptors, they open modality-gated channels. Local receptor potentials are generated when the peripheral receptors of a sensory neuron are stretched, compressed, deformed, or exposed to thermal or chemical agents. So local synaptic potentials are generated when motor neurons and interneurons are stimulated by input from other neurons. So you're generating local potential. If it's a receptor potential, it's a change to that peripheral receptor. If it's a synaptic potential, it is stimulated by input from other neurons. Okay. So local receptor potentials cause modality-gated channels to open, and they encode the sensory information into a flow of ionic current. So local potentials travel just that short, 1 to 2 millimeters, and the amplitude decreases with the distance traveled. So the strength can be increased and potentials generated by temporal and spatial summation. So spatial summation is where either receptor or synaptic potentials are generated in different regions of the neuron and added together. So we're getting input from a lot of receptors or a lot of other neurons, and all those added together create a larger potential for depolarization. Temporal summation is the series of small potential changes that occur within milliseconds of each other. So each that particular receptor or synapse is being stimulated over and over again, and that's what makes it temporal. So it's the same thing happens many times. versus a lot of things happening all at once. So spatial versus temporal summation. I hope that makes sense. So action potentials, because the receptor and synaptic potentials only spread a short distance, the action potential is essential for rapid movement of information over long distances. So the action potential is a large depolarizing signal that's actively propagated along the axon by repeated generation of a signal. Because it's actively propagated, the action potentials transmit information over longer distances than receptor or synaptic potentials. So I really like this chart in the book because it shows the depolarization and repolarization in conjunction with what's happening with the gated channels. So we'll go through each one of those in a minute. So the meaning of the signal that's sent after you generate an action potential is determined by the neural pathway. So if you have a neural pathway that's ending up at a neuromuscular junction, it's going to result in a muscular contraction. If you have a neural pathway that's ending up at an endocrine cell, it's going to result in the release of hormones. So the meaning of the signal is determined by the neural pathway. The action potential is all or none. Every time sufficient stimuli are provided, an action potential will be produced. Stronger stimuli produce action potentials of the same voltage and duration as minimally sufficient stimuli. So it's sort of like once the water starts to boil, you're at boiling temperature until all the molecules get converted to steam. So it's the same thing. If you have a stimuli that's minimally sufficient to create an action potential, you're going to get the same stimulus as you do from a stronger stimulus. If you have more of them, of course, you're going to create more action potentials. But you only need the minimally sufficient amount in order to create that action potential. So the action potential is produced as a sequence of 3 events. And this is the graph that is a couple slides back. This graph, love that graph. So we get rapid depolarization of voltage-gated sodium channels open. And then we get a decrease in sodium conduction and the channels close. Then we get rapid repolarization where voltage-gated potassium channels open. And so in the diagram, at the resting potential, both of the gated channels are closed. Let's go back to the diagram. And if you can't see this, you'll find this in the book. I think it's figure 5.8. But the figure numbers don't quite match between the electronic version and the paper version. And when I'm recording these lectures, I only have access to the electronic version. So it's probably figure 5.8. But it's very recognizable. You'll be able to find it. So at resting potential, both sodium and potassium voltage-gated channels are closed. When you reach a threshold potential, enough to generate an action potential, the voltage-gated sodium channels open and sodium enters the axon, beginning to depolarize it. So depolarizing it, we're making it less negative than it was before. When the cell gets depolarized, more voltage-gated sodium channels open, and sodium rushes into the cell, depolarizing the membrane. The sodium channels close about 1 millisecond after opening, so 1,000th of a second. So they just flash open, boom, they flash closed. When the sodium channels close, we start to get repolarization, and voltage-gated potassium channels open. The potassium exits the cell, taking positive charges out of the ion, taking it back down to its negative resting state. The voltage-gated potassium channels remain open. The cell gets a little hyperpolarized, where it's a little more negative than it is at resting. And the potassium continues to leave the axon, and that restores the polarized membrane potential. So the sodium-potassium pumps are also working and the leak channels are also working to restore that potential. So the brief hyperpolarization of the membrane results in the potential becoming more negative than the resting potential, and later the cell membrane returns to resting potential after all the membrane channels are closed and the sodium and potassium pumps in the leak channels do their job. So you have a little bit of time when the cell is hyperpolarized. Okay, so the threshold stimulus intensity is the stimulus intensity sufficient to produce an action potential. So it doesn't need to be really super big, it only needs to be enough. So 15 millivolt depolarization, which is a change in the membrane potential from minus 70 millivolts to minus 55 millivolts, is typically sufficient to trigger an action potential. So it really doesn't need very much depolarization to shoot off that nerve signal. So that's nice, right? So the refractory period is the period of hyperpolarization during which the membrane potential is even more negative than the resting potential. So at that point in that refractory period, it is difficult to initiate a subsequent action potential. So the refractory period is defined by the ion channels. Some ion channels, like those sodium, voltage-gated sodium channels, become inactivated immediately after opening, and they require a specific amount of time before they can be activated again for a subsequent action potential. So they open, sodium rushes in, they close, and then they have to rest a little bit before they can open again for a new action potential. So the refractory period is divided into two distinct states. The absolute refractory period is a point at which the membrane is unresponsive to any stimuli. The relative refractory period is the membrane potential is returning to the resting level. It might be a little bit hyperpolarized, but with sufficient depolarization, you can get through that relative refractory period and generate another action potential. So during the absolute refractory period, the membrane is not responsive to stimuli. Some axons might be specialized for faster action potential progression because of two structural adaptations: increased diameter of the axon or myelination. So the example that they give in the book is the water and hose example. A wider hose will pour more water in less time. So a fire hose is going to pour more water in less time than a garden hose. And tape or myelination around a leaky hose will concentrate the flow. So that's sort of our example how increased diameter of the axon and myelination are going to increase the time, or decrease the time really that it takes to generate another action potential. So I'm going to end this part of the lecture, and in the next part we're going to start to talk about myelination and how that helps increase the faster action potential.